Everyone, I am Ramya Prabhu from Data Science branch. So today our topic is gradient descent visualization. So gradient descent is an optimization algorithm to minimize the cost function in machine learning models. In this experiment, we use simple linear regression to predict study exam scores based on everyone. I am Ramya Prabhu from Data Science branch. So today our topic is gradient descent visualization. Gradient descent visualization is an optimization algorithm for used to minimize the cost function in machine learning models. In this experiment, we use simple linear regression to predict student exam scores based on their study hours. To implement and visualize the gradient descent algorithm for a simple linear regression problem using a real world dataset. The objective is to observe how different learning rates affect the convergence of the loss function during training. So here we have used some tools. They are Python 3.10, Pandas, NumPy, Matplotlib, and skitlearn, sklearn. Pause ಮಾಡಿದ್ಯಾ?
Hmm?
Advantages of gradient descent works for complex models, can optimize parameters for models where analytical solutions are not possible, scalable for large datasets, variants like SGD or mini batch GD handle large datasets efficiently, adaptable learning rate. Modern optimizers improve gradient descent by adjusting learning rates dynamically for faster convergence, efficient for high dimensional problems, performs well even when data has many features where direct computation of derivatives is complex. Visual interpretation. Gradient descent helps students visualize the path of optimization and convergence toward a minimum. So disadvantages of gradient descent are learning rate sensitivity, local minima problem, requires careful tuning, computational cost, convergence issues. So these are the disadvantages of gradient descent. Continued by Kavya.
Now let us see the code. Here is a brief introduction of our code. Uh, Now let us import the libraries. Import NumPy as NP. Import NumPy for fast numerical array operational and math. Import Pandas as PD. Import Pandas for reading and manipulating tabular data. And next is import matplotlib.pyplot as PLT. It plotting interfaces for creating figures and charts. Import OS. Import the OS model for interacting with the file system, and it is not used later in this statement. Now let us read the data. Data equal to pd.read csv sample1.csv file. Now here we read the CSV file, that is sample1.csv into a pandas data frame named data. Next is x equal to data of hours dot values. Extract the hours column from the data frame and convert it into a numpy array x. Next is y equal to data of score dot values. Extract the score columns and convert it into a numpy arrays, that is y, that is a targeted output. Next, let us see the step 2. Gradient descent function. Def gradient descent of x comma y comma lr dot iterations. It defines a function gradient descent that takes input of x, y learning data, that is lr, and number of iterations. M comma c equal to 0.0 comma 0.0. It initializes the slope and interrupts c to 0.0. Next is n equal to len of x. It computes the n, the number of data points, that is length of x. Next is cost of history. It creates an empty list to the record cost, MSE, that is mean square error at each iterations. Now, for I in range of iterations, it loops the iteration times to iteratively update the values of m and c. Y predict of m into x plus c. It computes the predictions of y prediction for all inputs using the current line parameters. Next is cost equal to 1 by n into np dot sum of y minus y prediction into 2. It calculates the mean squared error, that is MSE, cost for the current predictions. Next is cost history dot append of cost. It append the current cost value to the cost history for later plotting analysis. dm equal to minus 2 by n into np dot sum of x into sum of y minus y prediction. It computes the gradient of the cost with respect to the m, that is the partial derivative. dc equal to minus 2 by n into np dot sum of y minus y prediction. It computes the gradient of the cost with respect to the partial derivative. Next is m equal to lr into dm. It updates the m by moving opposite in the direction scaled by the learning rate, that is lr. C equal to lr into dc. It updates the c by moving opposite the gradient scaled by the learning rate, that is lr. And it returns the values return m comma c comma cos history. After all the iteration, it returns the learned slope m, intercept c, and the cost history. Now let us see the step 3, which tries to multiply the learning rates. Learning rates equal to 0.1, 0.01, 0.05. It defines a list of learning rates to compare the values of 0.1, 0.01, and 0.04. 5. Iterations equal to 200. It sets the number of gradient descent iterations to run for each learning rate. Next is PLT dot figure of fig size equal to 10,6. It creates a new figure for plotting with a width 10 and height of 6 inches. For LR in learning rates, loop over each learning rate value in learning rates. M, C, cos history equal to gradient descent of x, y, LR of iterations. It run the gradient descent with the current LR and store the return slope, intercept, and cost history. PLT dot plot of range of iterations is cost history label equal to L, f f of LR equal to LR. It plots the cost history of y against iterations index of x and label the curve within its learning rate. Next is PLT dot title of gradient descent convergence for different learning rates. It sets the plot title describing what the chart shows. Next is PLT dot x label of iteration. It labels the x-axis as iterations. PLT dot y label of cost of MSE. It labels the y-axis as cost of MSE for finding the mean square error. PLT dot legend. It displays a legend that maps each plot and curve to its learning rate label. Next is PLT dot grid of true. Turn on grid lines for easier visual reading of the plot. Next is PLT dot show. It renders and displays the figure in your environment. And this much it annotates the code plot to save the figure. Add the code to the print final MC for each linear regression, or show a short example with the dummy data so we can run it immediately.
Line for best linear rate, where best LR represents the learning rate step for gradient descent to zero point 0.1. The value view previously found works best, and m comma c comma underscore is equal to gradient descent braces x comma y comma best LR comma 1000 represents uh, calls your custom gradient descent function input feature x y and best underscore lr and 1000 iterations. It represents the 1000 iterations. Next comes y predict. This code snippet is used to predict the score of the gradient descent. And next is to show the graph we use a matplotlib where we define it as plt dot figure, where figures as will be 10 comma 6, and plt dot scatter. The type of the graph is a scatter plot, and original data point as a scatter plot to show the real study hours versus exam score, where study hours is labeled as X labeled, and exam score is labeled as Y label, and plt dot show shows outputs the graph and shows you the final graph design. Next comes Next comes print the linear slope and intercept, and what is the slope in 3 decimal it will print as shown in this code snippet. Next comes the step 5, comparing with scikit-learn linear regression. First we should import the linear regression from scikit-learn library, then convert x to a 2D array of shape required by the scikit-learn. It explicitly a 2D feature matrix. Next, x reshaped. This is used mainly for to reshape the model in a 2D feature matrix. Next comes the it is a model object where we take the linear regression library as to fit the data. Initially computes the best slope or intercept using the normal equation. Normal equation means exact solution. Next, it prints the scikit-learn linear regression and shows you the output. Next, explained by Abhishek. Let's run the output.
Tested our gradient descent algorithm with a learning rate of 0.01. After the several iterations, the slope and intercept values stabilized at 7.282 and 9.639. When we compared these with a skit-learner's linear regression model, the results were almost identical, 7.263 and 9.765. This close match shows that our manual gradient descent implementation is correct and effectively minimize the cost function. The visualization clearly shows the cost value decreasing the over time, which means the algorithm successfully converges to the optimal solution.
Thank you.
Thank you, everyone. This is the figure one graph. The next one is this is the second figure of this gradient visualization.